All right, so let's get started. Okay, so let's just do a few heads up before we get into the course. So first of all, like we have announced the time slot for the paper presentation, so please register time slot before September 17th. Otherwise, we will randomly assign a paper and a time slot. Oh, sorry, not a paper. Actually, a paper you can just fill it in 1 week before your presentation, but we will randomly assign a time slot for those who do not register. So please go to register before September 17th. And last week we point out there's a participation score. If you ask a question, make questions in the class, you can get 2 points per question and maximum 6 points. So here's the rule. So after asking your questions, no matter on the chat box or you come to in person to ask the questions, then you can send us an email. So here is our email, like always.oxhollet@gmail.com. So the content should include your name, student ID, that of the class, your question in class, and a screenshot of your question if you ask via the checkbox, because we have a WebEx, and if you are going to ask a question on checkbox, it is also welcome. Okay. So for the paper presentation, each group should join online when you need to do the presentation at a week. So in other words, if you are not a group that you need to do a presentation, then you don't really need to. It is not mandatory to join the WebEx, but yeah, optional. So the presentation will be online every Friday. So I think the time will be like 10 to like 11:30, according to your time slot. So what do we expect for the presentation? Because the presentation is super short, it's only like 68 minutes. So here's the things that we are going to expect you have. Oh. So first is about the background and trend. Like this you may get a lot variety of paper from different operating systems or different systems. So we might need some background to understand what this paper is about, and also the trend. So it is about like 2 minutes. So like 1 to 2 slides are enough. And then related works, observation and motivation is very important for your presentation, because without this, we cannot know how advanced, how novel this work is. So you can spend another 2 to 3 minutes on the related works of the observation and motivation part. So the rest of time is the methodology. So we accept methodology concepts, not the full methodology. So I mean, there might be a lot of algorithm or like data structures in the paper, but because you only have 6 to 8 minutes, so you need to try to keep it abstract, brief. So just give us some methodology concepts. What is the methodology about and how to link with their motivation? Okay, so that is enough. There's already 6 to 8 minutes if you follow this path. Okay, so here are some criteria. The first is to make the motivation clear enough. So organize the flow from background to real works and to challenge, make it clear. And it is good if you can use some like figures or animations to make the flow more clear. Okay, so the second one should be easy to follow. So please avoid to copy and paste a lot of text on the slides. Okay, so that is the second one. The third one would be, do not go through the algorithm, please extract the higher concept, otherwise we will not have go over time more than like 3 minutes. So if you do more than 8 minutes, then there have some penalty, then we will take 20% of your like score out of your presentation. Okay. So this is our rules for the presentations. So for you guys, if you have any question, you can just put your question on the chat box and I'll read it. So, okay. So if there's no question, then let's move on to our course today. So today, I think today is a very critical topic because we are going to do a quick recap of the operating systems, especially will based on Linux. Okay, so most of the things we talk today, there will also be in the rest of the weeks. I mean, there will be split to the rest of the week. So here's the agenda. First, we'll talk about the computer system organizations, how CPU runs the program and how CPU runs the operating system. So the second one is what is operating system and Linux kernel, what's the relationship between them, and what is the Linux kernel? Is it a process or is it the code or what is it? And the third one is the structure of the operating systems. So the general structures, and we will talk about how this topic, we'll talk about how this course will learn from processor interrupts, memory, I/O to file system. Okay, so first of all, computer organization. So this is our very basic computer organization. Like most of our devices, they're following the Von architecture. So we have the I/O device, memory, and compute. Okay. So the data usually should be moved from memory to compute, but now if there are too many data that cannot be stored in the memory, then the data has to be moved to the I/O device, and then the path will be moved like I/O to memory to compute. Okay. So this is the basic architecture in most of the, including server, PC, and also mobile phone, all the structure will look like this. So what is this so spatial? Okay. All right. Okay. So all of the code will become this kind of instruction. So you can image this is your C code, and instruction one is the very beginning of your code, and so then you follow up instruction three, blah blah, and those kind of instructions will be moved into the memory, or it can be a contiguous memory space, or it can also be not contiguous. Anyway, those kind of instructions will be moved to the memory before being executed by the CPU, right? So what we usually learn in our computer organization is there will be a register called like program counter. So the program counter will guide the CPU, or like you can think about will guide the AOU or control unit to access the next instruction that we need to run, right? So considering it, the program counter now points to instruction one, then CPU will fetch an instruction from the memory. So let's say instruction one, and then CPU will decode, execute this instruction. Okay. The thing is, after CPU execute instruction one, then this program counter will be automatically increment. So it will automatically increase to the next memory address. So according to what kind of architecture you are using, usually like you're using a 32-bit system or 64-bit system. So like it is a kind of the 8 bytes or like 4 bytes. So it depends. But this is very important because the program counter will be moved automatically to the next one and then the next one. So the thing is, if you have no like jump instruction, if there is no like branch instructions, then the program counter will just move to the third one, the fourth one, and then to the end of it. So this is the fundamental logic behind how CPU to run this kind of stuff. Okay. Sorry. All right. So because this software is like this, CPU only does routine work. CPU will only fetch the instructions related to where the program counter points to. And then program counter will be moved to the next slot automatically, like always 4 bytes or always like 8 bytes, so it depends. Because this kind of structures, there are several things that if you are going to run a program on your computer, like the computer will have several challenges if there's no operating system. The first one will be CPU will be solely occupied by one process. Come to think about, if you have two processes and then you compile them and then you run in your PC or your notebook, then after those two processes are, the instructions related to those processes are moved to the memory. So you can image here as the first process, like instruction 1 to maybe instruction like 1000, for example. And then from instruction 1001 to instruction 2000, let's say we have the second process. So according to this rule, actually the program counter will only move to the next one and to the next one. So when process 1 is running, process 2 has no chance to run, right? Because we have no operating system, there is no way to interrupt, there is no way to that process 2 has a chance to run. So this will be the first challenge if there is no operating system help. So the second one will be, we say there are I/O devices here. So if your code or like your application consumes a lot of memory and then the consumption is more than the memory capacity the system provides, then part of the code or like some of the data will be moved to the I/O device. In this case, when the data or when the instructions they are still in the I/O device, then CPU will be blocked, CPU will stop, CPU will stop to wait for the data be moved from the I/O to the memory. Okay, so in most cases, the I/O devices are super slow. You can think about the latency is around like 10 microseconds. It's a very fast I/O device. And usually, if you are using a hard disk drive, usually it's 1 millisecond. That is thousands of microseconds. Compared to those super slow devices, CPU is super fast. Like if you have a like 3 gigahertz CPU, that means for each clock cycle, the latency will be 0.3 nanoseconds. So nanosecond versus microseconds, this is a six digits difference here. Okay, because this is around very close to 10 to the 6 if this microsecond table. Okay. So if there is no help from operating system, then CPU will be blocked here and then wait for the instruction ready. The third one will be, actually, if you look at the structure, those are all instructions. So instructions are what you know, like you are going to load the memory address, you're going to store the memory address, or maybe do some addition, do some subtraction, those kind of low-level instructions. So there is no instructions called file, or like file open, file read, or like file write, right? So if there is no operating system help, there's no this kind of abstraction layers, CPU cannot understand what is a file in an I/O device. So for CPU can only understand is the memory address. So there are all like memory address there. Okay. So this is why if there is operating systems, then there is process scheduler to handle if there are multiple processes running in the systems, then how to negotiate which process can run first, which process has higher priority. And the second one will be, if we have the operating system, then we can have pathful handler, we can have context switch. So CPU doesn't need to be always locked by I/O device. We can have many choices here. CPU can be switched to run other process. And the next one is the file system. So with the help from file systems, the programmer, the users would have better, I would say like, it is more comfortable to access the store device by using this kind of file concept compared with the memory address. Okay, so those are what operating system can help with the whole systems. Okay, so let me reuse a figure. This figure actually I think is from your operating system textbook, and this is the rules of operating system. So before diving into the Linux parts, actually most of the concept and the rule of the operating system, they are similar across different like Linux, Windows, or like Mac. The concept is very similar. The difference is about the implementation is different. Okay, so the rule for the operating system will be it is a software layer stands between applications and computer hours, and the rule is to coordinate and manage hardware devices. So hardware devices including CPU, memory, storage, networking, most of the devices you can think about, they are all hardware devices. Okay. So I just briefly list several OS rules. I think it's quite important. I mean, there's at least here. There are more. If you ask ChatGPT, you can get a lot of a bunch of those kind of operating system rules. The first is about the transparency. With the help of the operating system, users do not need to worry about power management or conventions. Come to think about when you are writing Python program or like the C program, in most cases, you don't really need to know which real memory address you are touching, right? You don't really need to worry about if there are two processes, then how to negotiate which process use which memory slot. And you don't really need to worry about which CPU you are now using now. Okay, so this is because there are middlewares. There is operating system helps on this kind of coordination. And there are resource allocator. So resource allocator can better utilize those power devices. If we have a bunch of memory, if we have a couple number of computing cores, then how to balance those kind of resources, how to allocate those kind of resources to different processes, especially when there are multiple processes in your system. And the control program. So the control program is about to prevent errors and improper use of computers. Okay, I think this we will talk about it in the next few weeks about what kind of errors there are. Okay, so here are several well-known components that you already learned in your undergraduate. The first is about the process scheduler. So scheduler is going to fairly allocate CPU resource to applications, or you can think about the user process. The second one will be the memory manager. It allocates memory, locate patches, reclaim memory space. Okay, so those keywords here actually are those things we will learn in the next few weeks. So we have the lecture code process scheduler. We have also lecture code physical memory manager and virtual memory manager here. Okay, and then we will have block I/O there to manage I/O requests. And then there's file systems to locate file contents, partition device, control permission. All you will learn how Linux going to realize those kind of components. Okay, so figure on the right hand side is about the how is the position for those kind of there's device and there's operating system and there's a application. So just a very brief concept here. All right. So next big question. I mean, before these slides, we just summarized the things you learned in your undergraduate. There are a lot of operating rules and operating components. So coming back to our main topic, Linux. So what is Linux kernel? So this question depends a lot. I mean, if you put this question as what is Microsoft kernel and what is macOS kernel, the answer will be different. So in a Linux kernel, the definition will be a process manager consists of a bunch of C and assembly code. So this is a process manager. So actual Linux kernel is not a process. Okay. So there are several questions on the internet. People are discussing about is Linux kernel a process? So actually the answer will be no. It's not exactly a process. So here is the reason. So each process should have their own virtual address space. So this is the definition from operating system, right? But for Linux kernel, actually it shares the virtual address space with the user process. Okay. So I think before going into the detail about what is virtual and physical address space, I think I need to come back to the first sentence about what is a bunch of C and assembly code means. It means, for example, there is a process scheduler, you know, in the operating system textbook, right? So in Linux, there is a source code, also named the scheduler's code source code. So in the scheduler source code, probably it's the CPP or like some assembly files. So those kind of files, they are defining how the process scheduler works in Linux. So when we are going to run on this kernel, those kind of process scheduler files will be loaded into the memory, and then CPU will read those kind of file into the memory. Sorry, the file will be moved into the memory, and then CPU can run the code inside the file. So this is the reason we say like this is a bunch of C and assembly code. Okay. Okay. So coming back, what is the virtual address space? Before knowing the virtual address space, there is a counterpart, is the physical address space, right? So physical address space is the thing you know. We have DRAM. We put DRAM in the systems, and how large the DRAM is, then there is a physical address space. And the thing is, in current systems, in current x86 systems, in most cases, you cannot directly touch the physical address space because we have MMU. So in the CPU, there is a memory unit. So for your user program, your Python code, your C code, you will not directly touch a physical address space. Okay. Oh, this is going to tell you like actually the thing you learn from undergraduate, the patch frame is code for kilobyte. And the thing here we say patch frame and not patch is because for the physical address we call it patch frame, and the thing you know about the patch is for the virtual address space. Okay, so virtual address space is like this. For process A and process B, they all have their own virtual address space. Okay. So when you are writing the C or Python or some other like user level codes, actually what you see is this address space. You can always start from the very beginning of the address space and then to the end. You don't really need to worry about if there are other process will use your memory, because it won't happen, because each process has their own virtual address space. And the good thing is because if there is a virtual address space, then programmer can have more friendly to do the programming. So what operation does is to link the virtual address and the real DRAM address. Okay, so this arrows means there is a transformation way, and this transformation way we call it patch table. So with using the patch table, it can link between the virtual address for each process and the real DRAM address. Okay. So usually there will be no contentions in most cases. This is because operating system will help you to avoid using the same like DRAM patches. And if there are some patches they can be shared between process, operating system will also control them. So in the next lecture from saying we'll talk about why there are some patches two processes will share the same like DRAM slots. All right. Okay, so there is the second thing for the difference between virtual and physical address space is when you are using the things called always swap. Like in Linux, you have a function is called swapping. As if there is no free space in your physical DRAM, then you configure the storage device as part of the DRAM extensions. Then this is called swapping. So under the management of operating systems, those swap space or like store space taken up by hard disk drive or SSD will get physical address. So like this. So they all have physical address. So in this case, there is a data, and the data is moved from the RAM to the storage. We call it a swap. In this case, virtual address space, process B's virtual address space will be modified to like this. So we can change B's hash tables, and then process B doesn't need to know the data is swapping. So no code is changed, but actually the link will be, I mean, this slot can be remapped to this address. Okay. So in this case, process B doesn't really need to know where is the data is. Is it in the DRAM or is it in the storage device? Because for process B, it only knows here the data. We can get the data by accessing this virtual address. And then process B send the virtual address to the operating system. Operating system will help you translate into the physical address. So CPU will get the correct data from the storage device. Okay, so this is about the difference between virtual address and physical address. So coming back to our questions. For Linux kernel, actually each kernel doesn't have their own virtual address space here. This virtual address space for Linux kernel is shared with the user process. Okay. So what does it mean? It means like this. Assuming this is the virtual address space here, and then usually like if this is a 32-bit system, you will have 4 GB virtual address space for each process. But if you are using a 64-bit systems, then you will have a lot. So for this example, like the virtual address space will split into 2 parts. The top part is a kernel address space, and the bottom part is the user address space part. So user address space means those user program process data, they are in this area. Okay. And the thing is, sorry. So the thing is, the kernel, most of the kernel functions and kernel data, they will be placed in this area. And this is the reason why we say for the Linux kernel, they don't have their own virtual address space, because this is one virtual address space. And originally, this virtual address space is belonging to process B. Process B is a user process. But the thing is, part of the virtual address space, they are used to store the kernel source code. So here, because kernel is a bunch of C and assembly code, so most of the kernel source code they are putting in this area. So in this area, you can find like the address, scheduler code, memory manager code, file system code, networking code, block IO code. Most of the things you can image in the operating systems components, they are all like the file. So they will be put in this area. Okay. So kernel runs as part of a user process. A specific part of all process virtual address space points to the same physical address stored in kernel code. Okay. So let's look at the right-hand side here again. So when CPU now is executing the user program, so which means the instruction in this area will be moved into CPU for quick execution, right? And you can look at the CPU here. In most of the Intel CPU, there is a register to identify CPU now is in the user mode or kernel mode. So in the user mode, it means CPU can execute the data in the user address space, or we call it user program. So if there is a patch fault means the data is not in the main memory usually. So we need to get the data from the storage device, but it is too slow, so we need some help from operating system. Okay. So when there is a patch fault, then CPU will change the user mode to kernel mode. And because this is a register, so actually you can think about it's just only a bit change from like bit 0 change to bit 1. Okay. So after changing the mode to the kernel mode, CPU has the permissions to access the code in the kernel address space. So let's say there is a thing called patch fault handler. So patch fault handler means there is probably a C file, and this C file is going to handle the patch fault. So this is called the patch fault handler. So you can think about here is a C file, and then inside the C file it says so how how to handle this kind of cache load offers. Okay, so CPU will start to execute from the first address space, from the first address, and then second one, and third one, and fourth one. Okay, so this is logistic of how CPU execute user process and Linux kernel. And this is also the reason why we say Linux kernel is not a process, because if Linux kernel is a process, then CPU should do the process level command switch. Process level command switch means you need to switch from one virtual address space to another. So coming back to this slide, if Linux kernel is a process, for example, if Linux kernel is process A, and now user B is executing, so CPU should switch from this virtual address space to this virtual address space. Then there will be a lot of registers and there's a lot of data to be changed. Okay, so the overhead will be higher than current Linux implementation. So this is one of the reasons why Linux choose to put their kernel, also like merge their kernel address space with the user address space. So for user B, part of the user B's virtual address space, they are used for kernel. Okay, so in this case, we don't really need to do the process level command switch. But what the CPU only does is the mode switching part, and there's only very few registers switch from the user mode to kernel mode. Okay, so CPU switches to kernel mode to access OS code, but CPU does not need to switch the context. I mean the process context. Or you can think about context is just like an environment to run the process. So you need different CPU register, different memory, different memory settings, and different I/O settings for running different process. But in this case, CPU will not need to change those kind of stuff because for the CPU is still on the this user process context. Okay, so this is how Linux kernel run. Okay, maybe this is a little bit complex. So I just make a very toy example to let you understand easier. So let's say we have a submarine. Okay, the submarine means one process. So we say process A is a submarine. Okay, and the submarine is on the surface of the water. So we say when the submarine is on the water surface, we say process A is now running on the user mode. Okay, so your process will keep going. If it keeps going on the water surface, then it means the process now is executing in the user mode. So what does kernel mode mean? Kernel mode means process A dives into the water. So you can think about process A or this submarine is the same submarine. The only difference is the position of the submarine is different. So if the submarine is under water, it means the submarine is now in the kernel mode, executing the OS kernel. And if the submarine is above the water or on the water surface, then it means the submarine now is in the user mode. It can only execute the user process. So this one is going to answer as Linux kernel process. No, because process A is a user process. So when process A is executing, it just means the CPU is in the user mode. So when process A needs the help from the Linux kernel, then CPU will switch to the kernel mode. So you can think about we still stick with the same user process. The only difference is CPU has more privilege, has more permissions to execute OS code. Okay, so this is about the Linux kernel part. So any questions for this part? All right, so if there's some questions, then let's move on. Okay, but here's a caveat, because most of the stuff in OS, there are some special cases. So there are also some kernel process working on monitoring system status. What I mean kernel process is it does have their own virtual address space. So usually those things are used for the daemon, like to monitoring the system resource usage. Okay. But for the process scheduler and memory manager file system, in most of the case, they're not using this kernel process. They are using the concept what we just show you about. Okay, so that is. So following on, how to trigger or how to request kernel service? Because now we know the kernel. I mean, they're sharing the virtual address space with the user process. But how to trigger? How to request? I mean, if this submarine is true, then when will the submarine dive into the water and when will it go back to the water surface? So CPU runs the kernel only when some spatial events are triggered. Otherwise, it runs user programs or stays idle, basically. Here are a couple of spatial events. I think those spatial events you already know because in the very beginning of your undergraduate, people are talking about those spatial events. So for our events, you can also think about the signal, including the timer interrupt, the IO interrupt part. Okay. So software generated interrupts, including checks or exceptions, and it's a specific request from user process. For example, the system code we can use. And there are also some errors. So errors including like event memory access or pixels. So all of those stuff, including the hardware interrupts or software generated interrupts, it will trigger operating system to be run. I mean, it will trigger the CPU switch kernel to run the operating systems. And you can also think about, actually, those are all, they are all pairing together. For example, if there is a timer interrupt means inside the CPU, there is a timer. I mean, the timer will tick, and then we can know how long the process is running, right? So when timer makes the interrupt, then usually CPU will run the process scheduler. So when timer interrupt, CPU will execute a thing called timer interrupt handler. And timer interrupt handler is a bunch of the code. And inside this code, we can link to the process scheduler. So most of the stuff here, they have their own handler. So different handler will help to navigate, will help to detour to run in different service. So again, let's come back to this example. So if we have a user process called user process A, and user process A is running in the user mode in most cases. Okay, but when there is a thing called system call happens. So system call happens. What things will call system call? Usually, system call means when you are writing your C or Python code, and then you need some support from the hardware. For example, if you are going to read the data from the IO device, or you are going to get some data from the network. So your programmer will write this system code to that your user process has the privilege to get the help from this kind of hardware device. So system code usually, as the programmer, you can write your you can code the system code in your source code. Okay. So if there is a system code, then the submarine will dive into the water. It means CPU switch from the user mode to the kernel mode. After switching to the kernel mode, CPU will run the system call handler to handle the system call. Okay, so there are a bunch of system code. Usually, if I remember correctly, now we will have like 400 to 500 system codes. So different system codes, maybe it is about, for example, for file read, file write, and there's a lot of different system codes there. So different system codes, there is different system code handler. Okay, so after handling the system code, then CPU will switch back to the user mode. Then the user process will keep being executing. Then when process A running concept of O is consent, like if CPU runs too much of time, then the timer interrupt will stop this user process. Okay, so after the timer interrupt the CPU will once again switch into the kernel mode, and CPU will run the timer interrupt handler. It is part of the operating system, and this time interrupt handler will call the scheduler. So scheduler can switch the process. Okay, because scheduler will switch the process, so we will have another submarine. Because now we switch to another user process. We say different submarines means different user process. So now we switch to another user process. So here comes another submarine. And after switching the user process, CPU will switch back to the user mode to execute a new user process. We say process B. Okay, so now process B is in the user mode. So now CPU is executing the source code of the process B. So if process B needs some IO service, for example, there's an IO interrupt, including like keyboard, hard disk drive, those kind of stuff, then process B, CPU running process B will once again switch to the kernel mode and execute the IO handler. So in this case, CPU will once again run part of the operating system code. Okay, so this is the flow or like different spatial events occurs and how CPU handle it and what's the relationship with the Linux kernel. Okay, question? Yep. Yeah.
如果是说有一些经典的程式跟派克或者这样子，然后就是说让作业系统里面，比如说我的记忆体也好，或者也好，或者是在整个 kernel process 那些，比如说 intobed 这样子的话，那我们在整个作业系统里面有没有什么安全的，或者是说防止这种的错误的情形，或者是陷阱这样子？
Okay, so the question is, if there is a hacker, then if you're going to hack the operating system kernel and to make some like error inside, is it possible to prevent this kind of stuff? I think they are. The very general answer is actually when you are going to submit your operating system, then the operating community will review your code. So you can think about there's a Linux community. So each time when you pass your Linux source code to the Linux community, then there will be a very long code review to test about if you're uploading a patch as hacking or not. Yeah. So this path will be supervised by the Linux kernel like foundation. So this is not about today you have your own system code or you have your own like IO interrupt handler, then you just patch to the Linux kernel, then Linux kernel will accept. So in most cases, Linux kernel will reject because you need to follow the documents and you need to follow the rules about how Linux kernel, and also you need to upload your testing about like your code is not accurate code. Yeah. So I think this is a way for Linux kernel to handle this kind of stuff. The reason here is because for operating system, you can think about as CPU should switch into the kernel mode, switch into the privileged mode to execute it. So this should be make sure this code in most cases is correct. Yeah. So to make sure this stuff, we need to use the like human power to maintain this kind of stuff. Yeah. So this is quite different between the user and kernel process, because if this is a user process, then operating system can back up. So if there is some hacker code, then operating system maybe can help about to protect this kind of stuff. But usually, if the error is in the operating system kernel, in most cases, it is hard to debug, and it is hard to know where is the error. Yeah. So yeah, this is my answer for this part. Okay, so there is a question. I think there's a similar question is about if there is a very high frequency system code submitted from user process or other kind of very high frequency interrupt, will it block this kind of flow? I would say yes. If there is a very frequently system code be submitted or like frequently IO interrupt be submitted, that might happen. But currently, operating system has a couple of optimization to deal with this kind of stuff. So in most cases, I think you will not really block the system to make it hard to run. If there are process of user mode and the kernel mode, can CPU run them both at the same time? Does the CPU need to take turns to run? Good question. Actually, you can think about like this. In CPU, you have a lot of cores. So different cores, they have their own user mode or kernel mode register. So at one time, each CPU core, it should be either user mode or kernel mode. Okay. But for the whole CPU, I mean, you have different cores, so maybe some CPU core is executing the kernel and some CPU core is executing the user process. I think it's possible, but for each core, you can be only either in user mode or kernel mode. So, and in most cases, the priority of the kernel process or like the kernel code is higher than the user process. Okay, so yeah, that's about it. So after introducing the Linux kernel, let's come back to a higher level overview about the relationship between the user process, Linux kernel. Okay. So we have applications, right? We have a lot of different applications, example, database, PyTorch, those kind of stuff. They are all applications. So slightly below the applications, we have library. So libraries include C, C++, and a lot of different libraries here. And usually library, I think in most of the use cases for the programmer is the memory allocations. So for example, if you are using the C, if you are writing a C program, then you call the MALOC, the memory allocation function. It means you are going to call this kind of C library to do the memory allocations. Okay, so library is going to read out those kind of application user level requests to the kernel, because Linux kernel usually is a lower level design, so it is hard to directly interact with the applications. So usually we will have a lot of different library to wrap out those kind of details, low level details. It can be easier for the programmer to interact with this kind of library compared with directly interact with the Linux kernel. Okay, so you can see like this is the library and there's a system calls to interact with the Linux kernel. And the thing is, actually, in most cases, we will not directly call the system code. It is we will call the C library to handle most of the stuff we are going to interact with the hardware device. And the C library will translate to the system code. Okay. So for the core kernel part, actually there are a lot of stuff like memory management, process management, architecture specific code, and those kind of stuff. They are all, you can think about there are like 1,000 or like couple of thousands of line of code there, and you can check in the Linux source code about where is the memory management source code, where is the process management source code. Okay, and there are also I/O management. So I/O is quite complex because like there are a lot of different I/O, like networking, there's file, and there is a virtual file system, those kind of stuff. Okay. So those are all like the general operating system. And let me use 2 slides to point out some new like operating system design here. So we need to come back to one thing is our device, because operating system is designed to, you can think about it's going to serve the user process to access different kind of I/O device. So now when the I/O device changes, when there is a revolution of I/O device, probably operating system needs to be rethink. Okay, so in the year of 2011, like there are a lot of high throughput SSD, right? So after 2017, there's a little bit change. Like there are some NoSQL database comes into our life. So for example, like key-value database and those kind of database, actually what they need is latency. They're going to make sure each request to finish in a certain latency. So here comes ultra low latency device. So they are all SSD, but their design is a little bit different because on the left-hand side, it focuses more on the throughput part. So throughput part is more like how to finish as much as I/O requests as possible. And ultra low latency means for each request, we need to finish in like 5 microseconds or like 6 microseconds, those kind of super low latency. Okay. And after that, actually, there is a thing called storage plus memory. It's because we have those super fast SSD and this super high throughput SSD. So it's it possible to do the DRAM extension to integrate on this kind of DRAM chips to provide a super large memory capacity. Okay. And then this also changes for the data bus because you can see about the change for the PCIe from 2003 to like 2021, like we are from PCIe 1.6 to PCIe 6.0. So the bandwidth between the I/O device and memory, it also changes a lot. Okay. Oh, I think it's break time. So maybe let's take a 10 and come back later. Hi. Students to the extra students, if you have a special reasons to add now, then I can give you a privilege, but no, because there are still 10 to 15 students that are waiting in the waiting queue for adding. But if you are a perform program and you must need to get this course in this semester, then I can give you a privilege. But if there's not this kind of reasons, then yeah.
Do you offer this every semester?
Every year, because next semester will be another professor, but it will be the same topic on operating systems. Yeah. Yeah. Thank you.
因为我上礼拜因为实验室都是没办法来，希望还有办法加签。
现在不行，因为现在有10几个人还在等，
在等哦。
等 Q。
好，
对对对，
谢谢。
不好意思。
而且那个
报告
也是感谢。
可以是个领准，可以是个领准。对，谢谢。
你好，那个我是因为那个家庭是抽签那个，我是下一个下，就有没有办法在就大概是
下一位吗？好，你寄信给我好了，我帮你处理一下。好，谢谢。
就是这边的优势有这个 kernel space，然后您说这边有个 C library 需要用 system call 去跟 kernel space 做交流吗
C library 基本上都是用 system call 去跟克隆 space 做交流，应该没有例外。我目前想不到例外。
可是之前你们说的是 system call，比如说是 arrive 或者这，所以 system call 是怎样的一种词汇
？system call 是有点像是，有点像这样的，就是要怎么因为它有点像这个指令，就是跟不同硬体装置沟通的。那 file 的 rewrite 就是很基本的，就是对 file 的指令。那它可以是 system call 是个集合，就是它跟这个数百个不同指令集合在一起，所以一个 file read 跟 file write 它就是分别对应到一个 file read 的 system call 跟 file write 的 system call 这样。
所以比如说那有什么 C library 是，就你可以举一个比较
every 的 every 就是用 every 的底层实作就是去 call kernel 的 system call， 对，它就会 call 那个 system call 的那个号码，然后就可以直接对应到 OS 就会知道说你是要执行这个 system call。
OK， 那还有这边就是这边的那个memory management、process management 这些东西是应该是
core kernel 里面
core kernel， 那上面的部分是
上面这个部分里面大部分是属于这个 driver 部分比较多。这边的 VFS 跟 file system 也是算 kernel 里面的，对，只是我没有写有对啊 I/O management， 对，这个都是算 I/O management 里面。
所以1、2、3、4这5个是属于
对，这5个是就是 core。
那这个是属于这个就是这个
driver，
那这个 networking，
我觉得它这边话题是因为它的定位应该是那个 我觉得它定位比较广，因为它的 networking 它是可以属于 driver 的部分，那也有属于硬体的部分，这样子。就是它的 networking 这边比较模糊一点点。对。
哦，还有就是对前面去介绍那个呃那个 kernel 的那个定义的时候，
应该是在下面。
我就这么记吗？还是说我
对，kernel 定义。
对，就是因为我记得您有解释一下为什么我可以这么理解，但是那一段我没有很听得懂。
哦，你是说为什么它是长这样子吗？
对对对，
因为其实这基于下面这些有没有的东西，
可是您讲这个的时候是，因为这是 variable，是因为您介绍 variable 是因为您想去解释什么叫 virtual。
我想解释的是为什么 kernel 不是一个 process， 因为一个 process 需要有它自己独立的 virtual address space，
但是它的
但 kernel 没有。
那 kernel 只是在一个 virtual address space 的其中一个部
对，
分。
它是共用的，对，它是跟 user process 共用，就是这里这个一整个是一般 user process 的 address space， 但它的上半部会切出一部分给 kernel 用。
所以说我就直接记什么 Linux kernel 就是个
对
process manager，就是包括是
对
C 的 standard code 就好了。
对，其实它不是一个 process，就重点就是它不是一个 process，
好，
它基本上就是后面那段，但是它的目标就是它是一个，
还是它这它 definition。
对对对对对对。
啊，还有一个东西就是这边 swarm 的时候，您说这边就它不需要去知道这个 data swarm，它那我是不是可以理解为，因为像 virtual memory 跟physical address space 的时候，这边相当于有一个是一个 virtual 到 physical 的一个映射一样的感觉，它只是把那个映射去改了，那个 mac。跟那这个东西 PTV 这个是
这个是 Linux kernel 里面对应的 library， 它怎么去 code 的？
怎么去 call？
对，就是这个 BT to stop dash entry 这件事情是去更改，就是他怎么知道它是这样 code 过来的？
其实它不只是改那个 page，
page table 的这其实比较细节，就是它这个 page table 其实它做了这样的调整，就是透过这行这个方选做这个调整。
所以我想在 page table 里改，就是用这行，相当于是在用这行，我就可以在 page table 去改。
因为它其实实际上不是真的去改 page table， 它是去把 page table 变成是 non-present， 然后透过这个辅助的函数去找到资料在哪里。因为 page table 里面并没有这一段对应 ，page table 都只会有上面这一段。对于 page table 来讲，它只会记录DRAM 里面的事情。所以这边我没有显露清楚，是因为这边其实它的 page table 是只被标注成 non-present 而已。
就是说目前在 RM 里面没有出现，然后我用了一个函式一样的东西去告诉它说，
没错，
哦，它在另一个地方。
没错，然后这就是那个函式的名称。
哦，对，发现了。
请问，就刚才这边讲到说 kernel 它不是一个 process，但是每一个 process 里面就会有 kernel space。
对，没错。
为什么？因为我很好奇说，刚才有讲到说，如果它自己是一个 process，然后变成在处理那个 process context 的话，就是 CPU 的。所以这其实 CPU 没有办法做到一些事情。
不是，是因为应该是说，因为 Linux 不想要让 CPU 处理 process 处理这件事情成为一个成本。因为如果今天你的 user process， 就像刚才有人问我，如果不想长抽时间扣的话，那如果我 kernel 跟这个不是绑在同一个 address space 的话，那我就要去切 table， 我就要去切 page table， 然后我就要去切那个一些 registers。那你切一两次没问题，可是你如果切很多次，对 CPU 来讲，它负担就会很大。但是如果它是共用同一个 virtual space 的话，它基本上就不太需要做这种事情，因为它就是同一个 process 上面，只是 program counter 从这边改到这边来的差别。
CPU 一直去切这个 process， 它的付出的代价是什么？
它的付出代价就是它里面的 register 全部都要再把它写回到 memory 去，然后换到另外一个 process 的那一包，就是它属于它的那些process 的资讯跟 memory 资讯，再把它写到 CPU 的 memory 里面去。当然，它这个速度可能会就是几奈秒就完成，可是对于 CPU 来讲，它的运算一次就是0.3奈秒，所以它就算只是几奈秒，对它来讲也是个10几倍的事情。 对，
所以我可以把它理解成，它这样子绑成一包之后，它得到的好处是 CPU 的 load 比较轻，但是
对
它的代价就是它这整一包的大小比较大。
它，你可以想象成就是 user 可以使用的 virtual address 变少了，就是实际上它的这个可能是个，实际上的地址是这个是个4G， user 其实只用3G， kernel 要1G， 可是这是32bit system， 但是现在的系统都是64bit 为主，所以其实就没有问题了，因为64bit 的话，它这边的操作空间其实很大，它只是一个256TB 之类的吧。所以其实一般来讲 virtual address 不会用到这么多。
一个 process 它的这个 kernel 大小是一样的。
是一样的，是一样，固定就是1GB。在32bit 系统里面是固定1GB的，但64bit 是不一定，64bit 它是动态被分配的。
那是什么？
就是其实它这个64bit 它是可以透过 kernel 自己去做调整，对。
是这样。
那就是 kernel mode 转 user mode 的话，就是它是那个 mode 是在 CPU 的 register 里面是吗？
对，
就假如说当我们例如我们在 user space，然后我 call 一个 system call 的话，我那个转 user 就转那个 mode 的程式是 CPU 会我只要 call system call 它就有 interrupt 的，
对，它就自动转，
它就会自动转，
它就自动转。
所以那个我们根本不用写什么 user mode 什么1转0 0转1，
没有，那个是 SQL 自己会做的事情，它是硬体做的事情。
对，还有一个老师就还有一个什么像你看，因为 kernel 就是我们 kernel 的话，它是共用在它是放在它的 code 是放在 process 里面嘛，
对，
所以就是然后每个 process 都是知道，因为 kernel 控制在 physical memory 里面有一个位置，然后因为它是只有一个嘛，所以大家都是知道同一个。
没错，所以那个地方是共用的。
那你说那个 kernel process 的话，它是有自己的嘛？
可能会自己，
所以 kernel process 就不是在 process 里面，它就是独立另外一个，
它就独立一个自己有一个就是独立的 virtual
它
address
就是
space，
它就是一个 process，
对，
然后只是因为它在背后处理一些，
对，
例如回收什么的。
就是对，然后它的权限需要是 kernel，所以叫 kernel process。它的权限需要是 kernel mode 才可以执行，因为我们一般的 user process 是 user mode。
它基本上就是在kernel，它整个都在就是像如果是这里，它整个都在 kernel mode，然后 CPU
没错，
在那
没错，没错。
然后还有一个就是，老师可以抱歉，那个有一个就是，如果资料太多的话，不是会 swap out 到那个 SSS。
哦，就这个。
对，
这边。
是指说，因为一般来说是每个 project 你都会先切成好几个 page 嘛，然后我记得是说 page 是不会全部把所有 page 都要放在 CD 口，是当我执行到哪一个才把移到。那假如说满的话，你 swap out 的它是 可以 swap out 任何不一定是 swap out 自己的，可以把假如说例如 project B 假如说要执行，然后已经满了，它可以把 A 的移开。
可以，因为这段是 always 控制的，所以它无关乎哪一个 process。
谁控制？
这段 swap 不是 always 控制的，是作用控制的，所以它无关乎是哪个 process。
那这个是什么？这是 API 吗？这是一个。
对，就是 kernel 的一个 function。
那这个是我要记起来我的 process 里面吗？
不用，这些都是
OS 自己
会自己
去做。
对。
哦，好，了解。好，谢谢老师。
好，感谢。All right, so let's come back. Because later there is a department meeting on 12, so probably we will need to finish our lecture today slightly earlier, like 5 to 10 minutes earlier. Okay. So I think there is one question from you guys. Okay. Okay, I think here, this is quite interesting for you, some of you guys is, I say like, for the virtual address space, not usually, always, for each user process, they should have their own virtual address space. But for kernel, they share their virtual address space among different user process. So you can think about like this. Let's put our system on the 32-bit system. I think it's quite simple. So on the 32-bit system, for each user process, you will have virtual address space. But the thing is, for user process, your own, you can only use a 3 gigabyte virtual address space because you need to let 1 gigabyte virtual address space for the kernel. Okay, and the thing is, because this is only virtual address space, so actually, this part for each virtual address space for each user process, they will point to the same physical address. they'll point to the same physical DRAM area. For example, why there are two different like virtual address that point to the same DRAM. One of the possibilities is maybe this is the kernel, maybe this is the kernel like data structure or like kernel functions. So for this part, it shares between all different user processes. Okay, so the thing is, what the design really sacrifices the virtual address space, not the physical. Because for the physical address space, we doesn't sacrifice anything. Because the kernel is still only occupied maybe, for example, the kernel core is maybe 60 GB. You only will occupy 60 GB of the DRAM area. And virtual address space, so because this is kind of virtual, so in a 32-bit system, what really limited the programmer is you can only address into at most 3 GB of the like memory. Okay. But the thing is, when we change from 32-bit system to 64-bit systems, the limited is removed because in a 64-bit system, actually, if I remember correctly, you can have 256 terabyte of the virtual address space. Okay, so 256 terabyte of the virtual address space, actually, they're weighing so much that most of the cases will not really use up those kind of virtual address. So in that case, this design will become an even better design because for the kernel address space, it doesn't really consume like, I mean, the consumption is ignorable. Okay, and why this kernel design their user address space, design this kind of integrated address space. The key reason is because if the kernel address space is separated from the user process, then each time when there is a process needs some help from the operating system, then CPU needs to do the process level context switch. So for process level context switch, CPU in most cases needs to dump most of the process related register to the memory and then to load the next process, let's say kernel process to the CPU. So this will consume a lot of time because you can imagine the moving between the CPU register to the memory usually is like, I think it's like 10 to 20 nanoseconds. But for CPU itself, like the clock cycle is only 0.3 nanoseconds. So the gap is still big there. Even there are all nanosecond scale, but there is still some performance overhead there. Okay. So I think let's move on. And I know there are some other questions that do not really answer in the chat box, but next time at the very beginning of the next course, I will try to answer them. So let's move on to our mem process. Okay, so we say actually the thing is for the hardware part, it changes a lot from 2011 to 2017 and even now 2025. I mean, device becomes faster and faster. So what should be changed? So let's look at this triangle. I mean, this pyramid, this hierarchy. We say we have the CPU cache in the CPU, and the extra latency is between 1 to 10 nanoseconds. So not only the cache, but also including the TOP there as some extra. So the latency is between 1 to 10 nanoseconds, and we say the CPU runs in the sub-nanosecond scale of like 0 point something nanosecond, depends on the clock cycle. And we have the main memory. So main memory usually back on DRAM. So the latency is between 10 to 100 milliseconds, depends on the access taken there. Okay. And we have storage device. So let's say the storage device is around 100 microseconds to 1 milliseconds before. Okay. Well, I mean before is before like 2017, before the advance of the ultra low latency storage device. So before 2017, actually the gap between the memory and storage is more than 10,000. Sorry, more than 10,000, not 10,000, more than 1,000. So in this case, operating system works well. But the thing is, if now the storage device becomes faster and faster and faster, so probably one day there is like currently now, like Samsung VNAND or like Intel, like DC SSD, low power, ultra low end devices, their asset latency is between 100 nanoseconds to 10 microseconds. So for this case, the question is, can current operating system really manage those kind of fast SSD? Okay. So actually the answer is no. So not exactly, because the operating system management overhead usually is 100 nanoseconds to 10 microseconds. What do I mean for operating system management overhead? You can think about if we are going to run a process scheduler, we need to CPU needs to switch into a kernel mode. CPU needs to load those instructions related to the process scheduler, and CPU needs to run those instructions related to the process scheduler. So usually, when we are going to reschedule a process, it will take around like 100 nanoseconds here. Okay, and then for some more heavier functions like context switch. So because context switch, we need to change a lot of stuff, including we need to change the process state, we need to change the cache table, we need to evict the data in the CPU cache, we need to do the TOB shutdown, we need to do a lot of stuff. So usually context switch is around like 1 microseconds. So 1 microseconds is around like 1,000 times more than one CPU's clock cycle, right? Okay, so in this case, if OS management overhead now is around 100 nanoseconds to 10 microseconds, and if we have some device, some storage device, some IO device, their latency is between 100 nanoseconds to 10 microseconds, then here comes the question. Then when CPU access those kind of super fast device, so CPU does this kind of IO management, because those kind of IO management is so slow. So in this case, it might be inefficient. CPU might spend too much of time to do in operating systems. So this is what I said, like here is a time to rethink the operating systems. Like storage response time catches up with the context overhead. Like storage response time now is around like 100 nanoseconds to 10 microseconds, and like context switch is also 1 to 10 microseconds. Not only context switch, but also like process scheduler, those kind of stuff. It is around 100 nanoseconds to 1 microsecond. So the overhead of running like file system, those kind of stuff becomes critical. So there are also some researchers that are talking about maybe we don't really need file system at this case. We need a new like in-memory file system at this case. We are going to minimize the operating system overhead here, because traditionally we don't really care that much about the overhead of the operating system, because the storage device is so slow. So even, I mean, your operating system is like 10 microseconds or 11 microseconds or 12 microseconds, it doesn't really matter. But now when the device becomes faster and faster, the time to run the operating system will really impact the system performance. Okay, and here are also some things other than the performance, like huge memory demands increase the deployment cost. For example, usually now we are using the 4 kilobyte cache size. Let's say we will partition the DRAM into a bunch of 4 KB area. We call it cache. But the thing is, now if our memory, especially when we have like ChatGPT now, and the transformer model, if it is running like the decoding phase, then the KB cache usually maybe it can go up to like 100 or even terabyte level of the memory consumption. So for those 100 gigabyte to terabyte level memory consumption, is it also a good idea to still using 4 kilobyte to manage it? Okay, so those are our open questions. Actually, what is the right cache size in this case? All right, so those are the recap part, and just use 2 slides to let you know there are some things we can rethink. And if we have some time in this course, then I will share with you some research, like results about those kind of topic. Okay, so process and interrupts will be our next topic. So here are stuff like we will include in those topics, like process descriptor, process state diagram, what are those in Linux, and then time it's not like like multi-table, debug, those kind of stuff. This time we're talking about how Linux really do the scheduling. So we will talk about the big O and big O1, and then CFS, those kind of scheduling. And then we will talk about the interrupts. So here are software interrupts and hardware interrupts. And we are going to understand how software interrupts works like and how to implement the software interrupts. So one of your hands-on as like in a system code part, just like how to add one extra interrupt in the Linux source code. Okay. So this is about the process and interrupt part. And then for the next part will be the main memory. Probably we will use like 2 to 3 weeks to finish the process and interrupt. And then we will move to the memory management. I think this part is a little bit complex because memory management, we can split into two very broad topics. One is physical memory, the other is the virtual memory part. So physical memory part is this part. So the real DRAM part. So I mean, if you insert like 4 GB DRAM, 16 GB, or even if you have a server, if you have like 756 GB of those kind of DRAM, then how to manage them? What we manage is how to allocate this kind of DRAM resource to your process. And also, because we have Linux kernel, so how Linux kernel can get those kind of memory, and how Linux kernel memory management and the user process management different between each other. Okay. So after talking about physical memory, we will move into the virtual memory. Virtual memory, just as we mentioned, each user process has their own virtual memory space. So most of the stuff we learn in the undergraduate, including the patching, page-fault handler, patch replacement, they are all in this category, the virtual memory part. But this time I'll do a little bit different thing as I will let you know how CPU does the patch table work. So like how CPU really access the memory and how to traverse the multiple label patch tables and how to access those kind of data actually without the help from operating system. Okay, so let's say about the like virtual memory stuff, and then if we have sometimes we'll talk about the LRU design in the Linux. Okay, and then here are some advanced topics, the memory hierarchy and the like NUMA, and then some like hierarchy stuff. So that is it. After that, we will move on to our third topic, IO device and IO system. So I think I will use like 1 to 2 weeks to talk about some IO device like hard disk drive and SSD. So for you guys already keep the memory storage systems, I think you'll be super familiar with this part. And then after the device part, the IO system part, we will talk about from the process, actually from the process in the user process, in the user space, when it is going to interact with the storage device, it will send the system code. And after system code, what would the system manage this request? So we will move to the virtual file system, patch cache, the file system specific block IO, block device driver, and device. So we will talk about between those 4 layers. What are those 4 layers in the Linux kernel and what's the implementations? Okay. So here are just some rundown about what we will let you know. So device driver, we will talk more about the interrupts, their top heads and bottom heads, and how to write the device driver. I think if I remember correctly, device driver will be one of your hands-on. And then there is a block IO layer. So what is how Linux kernel now works with the block IO layer. So we will have a history from the buffer to BIO, those kind of stuff. Okay. And then we will talk about the file system part. So file system including the file system specific and the virtual file system stuff. Okay. So we'll talk about the optimization of file system, what is files and what is directly in Linux, and how those kind of stuff work together with each other, and then what is the patch cache, how Linux maintain those kind of patch cache stuff, and then memory mapping, like how to store your data, how to store your file in the memory. Okay, so those are topics that we will talk about in the rest of our lecture, and I'll skip this part, the application part. I'll skip it. Okay, so let me switch the slides. I have another slide deck, but we still have some time, so let us move on this process and interrupts part. So first of all, we need to talk about what is a process. In Linux, a process is an active program and related resource, such as processor state, memory address space, and blah, 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 like file system state, those kind of stuff. So process actually not only is a program, I mean, it also includes the resource. So this is the reason why I say process table connection is expensive. Because not only we just move the source code from one to each other, we still need to checkpoint most of the register in the CPU and the memory address space state, those kind of stuff back to the memory, and then we need to load the new process state. So in Linux kernel, the process, most of the information that can be described by the things called text structure. So in your undergraduate, text structure is also called like PCB, process control block. Those are the same. I mean, in general, operating system, we call it PCB. In Linux, we call it text structure. So text structure, you can think about is a like structure, data structure. So inside the structure, there are a lot of fields. So like this field is called stat. So stat is kind of processor stat now. Is it the running stat, sleeping stat, or like what kind of stat it is? And then the priority of the process, what kind of priority it is? And then where is the parents and what is the task, what is the PID? Actually, you have a lot of more than those kind of information in the text structures. So task list is a kind of data structure in Linux kernel. It is a list of process descriptor in a circular double-linked list. So in Linux kernel, if we are going to check different user process like status, we can use this kind of task list structure to loop through all the process in the system, process state. Okay. So once again, each text structure means the state of each process. Okay. So we also call it process descriptor. Okay. So process descriptor contains all information about a process. So including the process ID. I think this is one of the most important stuff. A unique process identification value. Okay. So in Linux, the blah descriptor means the data structure for maintaining information for blah blah blah. The reason is, if you look at here, process descriptor. So process descriptor means the data structure for maintaining information for process. So later on, you will also learn like virtual memory management process descriptor. So it means the data structure for maintaining information for virtual memory management, or file descriptor. It means the data structure for maintaining information for file. So in Linux, different kind of descriptor just means the data structure file. Okay. Oh, here comes PCB. The process control block is a general name like we use in the operating system field. And process descriptor is the specific name we use in Linux. So in Linux, we call it text stack structure. Okay. Okay. So when we talk about this kind of text structure, this kind of stuff, we also need to know another thing is about the kernel state stuff. Because we say actually Linux kernel process in Linux kernel in most cases it use the same virtual address space with the user process. Okay. So you might heard hear about this kind of stuff about like kernel state. So what is kernel state? Kernel state in Linux is Linux kernel uses per thread memory area to store intermediate information and metadata block thread. Metadata block that the kernel not used to manage the thread. So what does it mean? It means now when CPU switch from user mode to kernel mode to execute the kernel functions, we still need some place to store this kind of, for example, the return for the kernel function or the like kernel function calls parameters, those kind of stuff. So we need some place in the memory, and the place is called the kernel state. So this is quite different because for the user process, we have the user state. And for kernel functions, we have the kernel stack part. Okay. All right. So intermediate information, including the return address. The return address means how to get back to the user process. I mean, we say we check from user process to the kernel to do something, right? But after finishing the kernel service, then we need to know where to go back to our user process. Where is the memory address is? And here comes the return address. So in this kernel stack usually it only occupies 1 to 2 patches. So it means 4 kilobyte to 8 kilobyte. So this area you can think about is one patch and this is second patch. So they are contiguous on the memory. So usually this is only an 8 kilobyte area. So in this area, it stores a lot of information. One of it is return address. So with this return address, CPU can go back to execute the user process. And also the kernel function call, this kind of stuff. And metadata block. So we also call it the thread information. Metadata block kernel user to match the thread. Okay. So a thread information is stored at the bottom of the kernel stack. So right here, this is the kernel stack, and here should be the thread information. So it is easier to access. Okay. Oh, here comes the size of the kernel stack. Actually, this will be a static configuration. It is around 2 to 3 packets, depends on different setting. Okay. Okay. So why we need this kind of thread information stuff? It's because this part is the memory used by the kernel, right? But now if kernel needs to know maybe what is the status for this user process or for other user process, so we need to link to the data structure used to describe different process. So the thread information here capture the reference we can get. Oh, where is the text structure list stored in the memory? So in this case, even the CPU is in the kernel mode executing the kernel stuff. If the kernel stuff needs to know what is the status for different user process, it is also possible to use this thread information to get to the data structure. Okay, so this is the basic part for the data structure used by the Linux kernel and the user process. Okay, so let's back to the user process part. So user process is the text structure part, and the first field is called state. So the state field of the process describes the current condition of the process. And there are 5 steps here. First is called test-based running. So running is a runnable step, either running or on a run queue. Okay, so this is the only state of a process executing in user space, or you can think about the user mode. So the second one will be the text interruptible or text uninterruptible. Both states, it is about the sleeping state. So sleeping means maybe some I/O requests are issued to the CPU. So CPU doesn't want to spend too much of time to wait for this kind of I/O stuff. So CPU will put the process into the sleeping mode, and someone will call it the block mode. Okay, so waiting for some conditions or waiting for some condition is the interruptible, and uninterruptible is the process is waiting for some condition, but it doesn't wake up, even receive a signal. Okay, this one is a little bit special condition, and we will talk about this one during the process creation. Just like when we are going to create a process, because it is a quite long process, so we don't want this process creation to be interrupted. Okay. So kernel thread will manage it periodically. Usually we use in the process routine procedure. Okay. And there are 2 different states, but I think it is not quite general to use those kind of steps. The first is about the stop. So stop is about the execution has stopped it. So there is a signal continuing to resume. So there is a step using this kind of continuous, we can resume this sub process. Otherwise, the sub process will be removed in the text structure. Okay, and there is the last one is the trace. So trace is quite tricky. Trace is a process traced by a debugger. So for a debugger to know which process is traced, the state will be changed to this kind of dash trace. Sorry, dash tab dash trace. Okay. So this is the life cycle for a process. So left-hand side is a concept. I mean, like when you are doing the general operating system, the left-hand side is what we have. And the right-hand side is Linux itself. So new in the Linux is existing task code form and creates a new process. So we can get a new process. Okay. And then the process will become in a ready queue for running. So on the left-hand side is the process is ready. Okay. So ready means it is able to run, but it depends on if there is no enough CPU capability to run the task or not. So if there are too busy in the systems, then there will be a lot of process in the ready queue. Okay, but even in this case, this step still be runnable, like text running. So text running there are two. One is ready but not running, or running. Okay. So the transition between the left-hand side to the right-hand side, already but not running to the running, is the schedule function. So the schedule function you can think about is the process scheduler. So the schedule function will cause the command switch to switch the state, to switch the process into a CPU or FPU. Then the state will still hold in the text running state. Okay. So in the text running, there are two cases. In the ready queue, not really run by the CPU, or it is running by CPU. Okay. And the waiting field on the left-hand side, interpret on the right-hand side will be two sets, interruptible or uninterruptible. So when the CPU needs to wait for the IO or some other special events occur, CPU will switch the process into the interruptible or uninterruptible state to let the process sleep a little while. And uninterruptible here is actually only this kernel can come to wake up the process. And interruptible means if the IO server is finished, for example, the hardware will return to the CPU to notify the CPU to say, hey, actually your data is ready. Then in that case, the text interruptible state will be switched to the running state. Okay. But if the process or if the thread, oh, here's some animation, sorry. So if the text is in the uninterruptible state, then we should wait for the Linux kernel to check for the state periodically. Okay. So this is slightly different because interruptible CPU can directly come to deal with it if there is a hardware event after. Okay. Okay. So the next part is the process family tree. Process family tree, if we look back to this kind of text like structure, actually each text, there is a field called parent. Okay. So for parent is, we should have the root ancestor, right? Otherwise there is no parent at all. So the root ancestor in Linux is called the init process. So the init process will be initialized when you power on your systems. So when an operating system is on, then there will be a process called init process. Okay. And init process, as for all the rest of the process in the system, they are descent of this init process. Okay. Because for the next process like PID2, PID3, we will fork the init process to get PID2, PID3. Okay. So this is the way how Linux works like. So how to access one's parents or children? So we'll use the parent or the children pointer in the text structure. Then the kernel can know, oh, which process is your parent process, which process is your child process. So with these structures, Linux kernel can easily access this family tree and to know the more information for each process. Okay, but the thing is, if we are going to access a process not on the same family, then it is still possible because we can, Linux kernel can look through all the text links. I mean, here, there is a pointer to chain the text links together, so we can also look through the whole list. In this case, even even the Linux kernel is not going to find the parents or child for a certain process. It is still possible by traversing through the text links. Okay, I think this is just some information to let you know. And here comes the more importance of process creation. Okay, so process creation, there are two main parts. The one is called fork, the other is called execution. So fork means to create a child by copying its parent. Why we say we are going to copy or fork? The reason is it can be efficient and simple. Okay, because creating a process, we need to give it a PID, we need to give it a text table, we need to give the text frames and signals, those kind of stuff. But if we can directly fork, if we can directly copy the text structure and we just modify the field for those kind of stuff, then the thing will be easy. And there's another stuff is if we can fork, if we can fork from other process, then it also means we can reuse some other process fields. For example, maybe some process are already terminated. It's a dead process, but it doesn't really remove by the system at the moment. Then the new process, in some cases, can directly reuse those kind of data structure. Okay, so in Linux, we use fork to create a new process. And then the execution is quite simple. The execution part is to load a new executable into the address space and route it. A new executable means like the .exe file. So it means like the file that can be directly executed. Okay. And you can also think about just like after doing the compiling, making those kind of stuff for a C program, you will get the execution file, and this file will be moved on the memory, and the CPU will start to execute it. Okay, but I think you will have one question about if we use this kind of fork and copy stuff, especially copy, because copy, it means we need to duplicate two data structures. So for example, we have the text structure, right? So if the text structures get like maybe a couple of kilobytes of the memory, then we need to duplicate this kind of data structure, and it might take time. So in Linux kernel, we use a thing called copy on write. Because naively, copying all resource from a parent process is time consuming. So the timing for reading to the copy is when we are going to modify the data. Otherwise, we can share the data structure with your parents. So how copy on write works? It delays and prevents copying data until the data is written. Okay. Otherwise, resources are shared in a read-only way. So here comes a quick example. So if we have a physical address space here, physical address actually is, if we have a lot of DRAM now, then there are data on those kind of DRAM. The data including the right-hand side is the process-related information like the heap, the stack, those kind of stuff, and we call it patch frame. At the same time, there are also operating system or Linux kernel-related data structure, for example, text table. Okay. So in current systems, we use packaging to evenly partition the LAN. So you can think about, we have a super large DRAM space, right? So we will partition this DRAM space into the same size unit called patch frame. So each patch frame will be 4 kilobytes. So with this kind of partition, it can easier for us to do the location. What do I mean location? Actually, there are virtual address and physical address. And virtual address, you can think about just like a mail address, right? So the physical address you can think about just like a latitude and longitude. Actually, the two are different, but there are some ways between them to do the translation. And this translation is done by the text table. So for the CPU, what it actually does is CPU will get this kind of translation by looking on the text table. So CPU will first load part of the text table into the CPU cache, register, and CPU will check about where is the translation from virtual address to physical address. So after getting the physical address, CPU can access the cache frame. Okay, so this is the typical way for Linux to work like. The thing is, if now we have another process called process 2, and process 2 is a child of process 1. So in this case, if we directly do the copy, then we need to copy all the page table information related to page 1 to the new address, right? And it takes a lot of time. Okay, so actually the thing is like that. If we are going to write some data to a new position, for example, this VA and PA, actually, if we are going to write some data to a new physical address locations, then at that time, we will copy out the cache frame. I mean, we will copy out the cache frames and we will modify this kind of page table information. This PA will be updated to point to this new physical address locations. So in this case, at the very beginning, we don't really need to modify all the cache frame. Sorry, we don't need to copy all the cache frame because page table usually there are several megabytes here, but each page frame is 4 kilobytes. So if you have a lot of cache, usually you are a large process. There are megabyte to gigabyte of the information there. If you at the first time you do if you at the first day you do the copy, then it takes a lot of time. But in Linux design, we only do the copy when the patch has been updated or being accessed. Write access, not read. If there's a read to a patch, then P1 and P2 will still share the same patch frame. Okay. So this is one example for copy on write. Actually, there are a lot more examples for copy on write. I mean, it doesn't really need to be the patch. It can also be, for example, the text structure. So for a text structure, actually, it can also be in a copy on write form. Okay, so I think let's stop here and let's regroup next week.
Is it possible to audit the class because I haven't updated from my
Yeah.
I need to tell TA to add it's free.
No, I don't think so.
We can just
Because we can also join online.
how can I get a virtual slides?
Oh, you're saying like if you are not registered in this code, maybe you can let me know and then I will add you into the E3.
Okay. Then I send you to later.
Yeah.
I think it looks like 还要 add 所以不同 page table 都有。
就是假设你有，因为你一个 process 也需要有自己的 page table，才有办法做自己的位置转换。
哦，
对，所以它的 page table 需要复制出来，但是 page table 一开始2张是非常是一样的 page table。那不一样的地方是等到它开始真的有存取的时候，它才会开始有动作。对。
所以page table 是会复制，但是 page frame 等到 write 才复制。
对。
OK。
我想问的是，这边的 read only 是指
read only 就是它被修改的时候 ，CPU 会被呼叫到。因为如果它不是 read only 的话，基本上就直接改就好。可是 read only 它是一个限制，就是如果今天我有 CPU 要存取这个地方的话 ，CPU 会有中断产生，所以让 CPU 可以进入就是修改这个的过程，这样。
所以我改的是那个，
你改的这个，就是你今天假设想要更改这个地方的位置的资料，可是你要先确认 page table 有没有这个资料，然后去做
因为我的
page table 维护。
应该说我想改 page table，但它只有 read only，所以我没有办法直接改。
对，
所以我得去弄一个 page frame，是一个新的 page frame，把原本的东西。
没有，不是，是你今天如果想要对这个 page frame 去做操作，但操作之前呢，你要先去找 page table， 知道它的位置在什么地方。可是你在找的时候，你会发现这个 page table 这张 page table 是个 read only 的 page table， 所以你没办法去改它的位置，因为你要把它复制出来，你才有办法去做写入动作。所以你会回去先去改你的 page table， 就是跟 always 说你今天要改哪个位置。 然后或者接下来呢，它就会帮你把这个 paper 复制出来，然后把资料改之后，然后再回去 paper 把这个位置修改成一个新的位置。
可是它不是 read only 吗？你怎么改？
就是它是 real 没错，可是 always 会把它在这个时间把这个 slot 把 the read only 全改掉。
所以
整张 table 是 read only，但是你今天如果要更改这个 slot 的话，你就需要把这个 slot 的，就是 read only 的那个 field 改成是可以更改的。
所以它还是会改。
对，就是只有这个地方改，其他就还是保持 read only 的状况。
改了之后原来的呢？
你知道原来的吗？原来不动啊，因为原来你说 P1 的吗？P1 不会动，因为它现在是 P2 想要修改自己的新的资料进去了，所以这时候就会出现 P1 跟 P2，它其实是会渐渐有不同的资料产生。因为你原本 P1、P2 其实是不同的 process， 但是你是共用的同样的P1 的资料。对。
那这就是个全新的，然后这个不动了。
这不动，对 ，P1 就不动。对。
所以我需要把这些东西全部 copy 出来吗？
没有，就是一个配角，就是4KB 而已，就是这个4KB 就会把它复制过来，然后你看你要改什么东西。
哦，
对，因为你这个一个 slot 对应到一个4KB 而已。对。
相当于是新建了一个新的，然后那这样这个没用了之后，它不动的话，它不会多余。
哦，不会啊，因为这是两个不同的 process。今天只是说为了方便，所以我这边直接从前面的那个 process 直接复制了一整份出来，然后作为一个新的 process 做使用。所以理论上前面那个 process 不应该被改到，因为他完全不知道自己的东西。你也可以这样想。
哦，
对。
那你先吧。
就是 straight infos 的真的实际应用是什么？因为你只有说有可能会去使用到，我想说它的
就是它对应就是如果你今天需要 user 相关的 user process 相关的资讯的话，你就需要通过对应去拿这些资讯。
对，那什么时候会需要？
你说，就例如你今天要知道这个 process 的 state 是什么，因为你要做排程，排程的话你要先知道每个 process state 是什么，你才知道说哪个 process 可以过去。可以单纯靠 kernel 是不会有这个资讯的，
对，
你就要进去对应去拿到你可以做排程的这一些 process 是哪些，你才有办法做接下来排程。这时候你就会需要透过这个资料卷去拿。
其实我没有听懂你之前说，它两个指针就知道同一个。
对。
我没有听懂这些。
哦，这个是你说这个嘛，就是这样会直过来。
你是说它就是位置一样，是因为它内存太大了，然后一个层一小？
哦，没有，这个是因为假设你像这两个 user 的 virtual address space， 对吧？这两个不同 process， 这是 process A， 这是 process B，可是因为它的最上面这边都是同样的资料，都是 kernel 的资料，kernel 资料是一样的。那这时候它在实体位置的时候，其实是只有一笔资料而已。那这时候还会透过
存的是位置，这个
你说哦，没有，指针是存在这个 table 里面，就是位置，但这边都是实际上的资料，就是这个是一个，这是一笔 address， 然后这是一笔 address 相似，然后是透过这个 table 去把指针指过来。
对，然后
对，
然后左边这个 A 和右边 T 是同一笔吗？同一笔。
你说这个吗？是位置？这个的话
是同一笔，那这两个呢？
这两个就不同，就是其他的基本上就是它就会知道不同的资料，就是实际上的资料是存在这里，然后这边都是一个一个的位置，就是你的例如4KB、8KB、16KB 位置，然后它透过转换就可以跟系统说它是放在实体哪一个 DRAM 的哪一个4KB 的位置这样子。
如果这样的话，相当于这个是 memory， 这个是 storage， 是吗？
没有，这些都是 memory 状况，这是虚拟的实体位置，就是实体的实体位置。Storage 是下一张图片才会出现的，我这边有。
不好意思打扰一下。
好，不好意思。
本期会议12点要开始了。
我
谢谢。
暂停一下。